Traffic jams and how to get rid of them. We start with 20 gizmo garden cars on a closed track implementing a car-following strategy. Each car measures the distance to the car ahead and adjusts its speed accordingly. Such a control strategy is called car-following, and it's what human drivers as well as adaptive cruise control systems do. Notice how cars start to bunch up in some areas, such as on the top left and on the right, while they thin out in other areas. After a while, areas of high density coalesce into so-called phantom traffic jams. They are called phantom traffic jams because there's no external cause such as an obstruction or distraction. These traffic jams, in fact, are not anyone's fault. Every driver is doing what makes sense based on the information available about the vehicle ahead. The chaotic behavior, with speed fluctuating wildly, is instead an emergent property of a string of coupled dynamic systems implementing a car-following strategy. Because of the stop-and-go nature of traffic under these circumstances, the average speed is lower than it could be if there were no traffic flow instabilities. Now we switch to bilateral control. The momentary drop in room light level is a signal for the cars to change their behavior. The blue LED indicates they are now in bilateral control mode. Bilateral control differs from car following in that it counterintuitively takes into account information about the car behind, not just information about the car ahead. As you'll see, the traffic flow immediately starts to smooth out. The dynamic system is working towards an equilibrium state where the cars are equally spaced and traveling at the same speed. Since now there are no cars stuck in a jam, the average speed is higher and the time to complete the circuit lower. Again, the momentary drop of room light was used to signal a change of state to the cars. The yellow LED now indicates they are back in car-following mode. Note that this time the initial state was almost ideal, with cars equispaced and moving at the same speed. So bunching up of cars can't be caused by initial conditions. Despite this, density fluctuations soon appear, and these eventually will turn into full-blown traffic jams. Once they appear, you will notice that the traffic jam moves upstream, that is, in a direction opposite to that in which the cars are moving. In fact, we can calculate the speed at which they move upstream based on the density of cars, the length of the cars, speed limit, and the control system parameters. One more time, back to bilateral control. Once again, the traffic flows smoothly and approaches an equilibrium state. The advantage of bilateral control are obvious. Note that this does not require full-fledged self-driving cars. Bilateral control is no more complex to implement than adaptive cruise control. The only difference is that adaptive cruise control is based on the state of the vehicle ahead, while bilateral control depends also on the state of the vehicle behind. Thus, distance and velocity sensors used in adaptive control to measure the state of the vehicle ahead need to be duplicated.